In this video we're going to look at how to build a type of radar device based on ultrasound, Sodar. And I'm counting this as a beginner's project because although it might look quite complicated, probably because there's a lot of wires about it, there's quite a few things on that breadboard, it's actually quite modular. And I'll show you how to build each stage a bit at a time and test it to make sure everything's working before your final project is complete. Well, let's get started. Is that it? So let's get started. First thing we're going to do is add a display. So we need our breadboard, we need an Arduino Nano, and a 128x64 LED display, and a collection of wires. Let's get started and get that done. So okay, that's wired up. We've got the 5 volts from the Arduino to the 5 volt rail. We've got the ground from the Arduino to the ground rail, could be a whale, the ground rail. And on the OLED screen we've got the ground to the ground, the VDD, VCC to the positive as well. And then the blue wire is the data. It's connected to the SDA, and that goes to the A4 of the Arduino. The clock is the yellow wire, so SCK from the screen going to A5 on the Arduino. So all we need to do now is to actually load up some demo code and give this a check. So let's plug in the Arduino already. I always test these when I get them delivered with the blink code, so they should have the blink code running, which it does, blinking the LED. So you need a couple of libraries to get these OLED screens set up. So if we go to Sketch, Include Library and Manage Libraries. And these little screens use a SSD 1306 chip, so we need that as a driver. Have we just caught that? Is it just a bit laggy? Yeah, it's a bit laggy. We'll go down to the Adafruit one. Obviously I've got it installed. There is a slightly newer version, which is why it says update there. If you've never installed this before, then you'll have an install button there. Just click install to install that. After you've done that, we need one other library, which is the Adafruit. And again, the computer's being really laggy, but they'll catch up. There we go, Adafruit graphics library, so Adafruit GR will be enough, I would have thought. There it is, right down at the bottom here. If you want to add in more letters, we'll get it up to the top. So there we go, Adafruit graphics library. Again, I've got it already installed. You just click there to install it. I can update if I want to, it won't make any difference. And once you've done that, you've got both libraries installed. You'll be able to go to File and Examples, down to where it says SSD 1306. We've got a 128x64 screen, and it's also R2C is the protocol we're using to drive this display. So select that, and we'll upload that to the Arduino. So it's loading now. We should see the screen come to life. And it's done uploading. It'll do a bit of a reboot. And nothing is happening. This is not unexpected. This is a common problem you will get. If you buy one of these screens from Adafruit, this won't happen. If you get one of these cheaper ones from China or wherever you source them from, then it's more than likely you've done all this and it won't work. It's just basically the address of this screen is different on these cheap ones compared to the Adafruit ones. When we say the address, R2C is a protocol that uses addresses, i.e. IDs that identify part on that R2C bus. Very simple fix. I've used around about a dozen of these, and they've always had a different address from the Adafruit one, and it's always been the one I'm going to show you now. So going back to the screen, you can see we've got the demo here. Scroll down to the setup, and if you look at this line here, it's passing what it says there, the address hex 3D for this particular display. However, I've never found it to be that on any of these cheap displays. I've found the address to be 3C. And that's worked for every single display. And I say I've bought about a dozen of these for various projects. It's always been 3C for me. So let's upload and see if that works. And we're uploading. Tilt it up a bit, because I'm expecting this to work. Come on. Still uploading. Done uploading. Rebooting. There we go. Adafruit demo, you can see. And it's going to go through the various things. So we now know we've got a working OLED screen that we can write to. The next part of our project is actually connect up the stepper motor and see if we can get that working also. So the next thing to do is to add the stepper motor, which is one of those. We're going to put it somewhere up the front like this, like that. Lots of extra wires, more than we actually need, but we're going to mount it somewhere up there. A bit of blue tack, stick it on the board. To drive it, we need a stepper motor driver chip, which come on these little boards. I'll put a link up in the corner now for my video on driving these stepper motors, and we're going to put that somewhere around there, I think. This simply plugs into there like that. Which way around? That way around. Like that. And we actually connect up some wires here, which will then go to the Arduino. The power for it, we're going to do is an external battery pack like this, or 5 cells at about 1.6 volts when they're brand new, 1.5 volts optimal. They're actually going to connect onto these connectors here for between 5 and 12 volts, because the Arduino, through its 5 volt connections off here, is not capable of driving a stepper motor. They take far too much current. So we'll have an external supply which we'll use to actually power the stepper motor under the control of the Arduino. Let's get that wired up. Okay, so here we have the wired up project. The stepper motor connector connects into that side of the driver board. I've blue tacked the driver board and the actual stepper motor to the breadboard. And we have 4 connections coming off this driver board labelled IN1 to IN4, and they directly go to any input pins you want, but for our code I've wired it up for pins 7 to D10. So IN1 goes to 7, IN2 to 8, etc, etc, up to IN4, which goes to D10, digital pin 10. And I've just tried, we just need to sort of pull that away. And all this is an elastic band that's just holding this wire in place. As I mentioned it just a little while ago, we have a lot of extra cable here that we don't need. So what I need to do now is add some external supply source to there. So we've got the battery pack here, 5 AA cells, gives us about 7.5 to 8 volts, depending on how fresh the cells are. We've got the ground pin there and the positive pin there. So we'll connect ground to the left like that, and this is all because the Arduino can't supply anywhere near the current required to drive this motor effectively. So we have an external supply which this board allows for. So that's powered up. All we need now is some demo code, which I'll show you where to get that from now. Okay, so we need a library first to drive the stepper motor. So again, go to the library manager and type in stepper. And the one you want is the one called stepper there. Again, obviously I've got it installed. So I'll select that and install that. And then if you go to my website, you'll find a link down below to the actual this project. And I'll put a link down below on the actual video as well now, popping up now. You will find, if you do that, this code here. So that's available on the website, and the links I've just described and shown. And we'll upload that to the board, and we should see the motor turn around. We need to stick on something so we can actually see it. So we'll stick on these wires just as little horns. So let's upload that. Okay, and off it goes. It should do a full 360 one direction, stop, and do a full 360 degrees. This is not easy for me to say, full 360 degrees in the other direction as well. Perfect. So the next thing we need to do is to get the actual ultrasonic device. We'll mount it on the front, but before we have it moving around and things like that, we'll actually just get it working so we can display a distance on screen just to actually check that the ultrasound sonic sensor is all working. And then we've almost got all the components we need to build this radar system. Now, one of the first things I have to decide, here's the actual sonar module, is how to mount it on the actual spindle of the stepper motor. So I had to look at it in a few different ways, and I think the way I'm going to do it, and people might disagree or do it in different ways, whatever you want to do really, is on the actual crystal here, I'm going to actually put some hot glue and just mount that and stick there like that. Hopefully that'll hold nicely, particularly if I do a lot of hot glue around there. And I'm going to bend these pins back, which I'll do now, so that when it's mounted on, they are facing straight out like that, making it easier to do connections to where they need to go on the actual Arduino over here. So let's just bend those back, and hopefully we shouldn't break anything. So 1, 2, they're not quite there, but in fact we should just do them all at once, shouldn't we? So at least we'll do these 2 at once there, and then we get all 4, which would have been a good idea doing it like this in the first place, like that. Not quite there. And yeah, that's probably going to do me, I think, maybe a little bit more. Okay, hopefully I shouldn't have done any damage there. I'm going to go and hot glue this on now, and then we'll connect it up. Okay, it's finished. Here it is. It's not pretty. Here we have a look. There. Lots of hot glue, but it's going to hold it in place quite firmly. I don't think I've fouled the shaft. We'll plug it in, we should be able to see it rotating. So we can actually put power on there. Nothing's going to happen because we actually haven't got power to the actual stepper motor, which, as we said, is from an external power pack, which we put on there. So black on there, red on the positive. These things are so fiddly and small when you've got huge gorilla-like hands, sort of. There we go. So that's going to do a full 360, which is obviously, it's no good, not when we've got wires connecting here that need to go over there. They're going to get fouled and tangled. And we only want, well, I only want to be able to see in a sort of 180-degree arc around here. So the next job is, what I want to do is actually make sure the sonar module's working okay. So I'm going to disable the rotation, and I'm going to unplug this in a second so it's facing forwards. And we'll wire up the sonar module and we'll give that a test. So we'll stop it there. Perfect. Okay, I've wired that up, and this project, rather like me, is getting less pretty by the minute. Obviously the wires are getting messy, but this is going to how it has to be, because you've got to have some flexibility. In fact, well, I'll tell you what I've wired up. Obviously I've put the positive of the ultrasonic sensor going to the positive rail. This brown wire, I know it should have been black really, but this is the ground going to the negative ground rail there. And then we've got the trigger and echo pin. Let me just check which is which. Yeah, I've got the trigger of the echo sounder connected with a yellow wire, and it needs to go to pin D12 on the Arduino, but this wire was a bit of a stretch to go. Just get that bit of point of view. It was a bit of a stretch to go all the way to where it needs to, and I still allow flexibility here as this rotates round. So as it rotates round, you want these wires to be able to move a little bit. So the yellow wire just comes down here, and I use another jumper yellow wire coming across here into D12. And I've done the same with this orange wire, which is the echo pin. So the echo pin comes down to here, where we've got another jumper going to actually D11 there. So we've got some flexibility when this moves round and about. We'll look at some code to test this, which I used in my ultrasonic range sensor. I'll put a link up in the top right now. So let's load that up. Okay, again to your library manager, type in new ping. And use this library here again, got it installed. So install that one, and then go to my website for the project page for this Sodar, and copy this code that you see here. Will be available on there, and upload it to your device, and we should see, where's my pointing pencil, we should see a distance displayed on here, which will prove that our ultrasonic sensor is actually working. So it's just compiling and uploading, and we should get some sort of display shortly of something centimetres, depending on what object it's kind of hitting. So hitting something reasonably in the distance over there. So I'm going to test it, put my hand here, And yeah, 4 centimetres, a bit closer, 2, a bit further away. And you can see my hand's going off screen now. Back again. So yes, it is detecting and ranging that distance to my hand. Fantastic. So the next thing we're going to do is actually rotate this 180 degrees either way. So we're all set up. I've altered the cord to actually rotate it just 180 degrees, because what we want it to do, here's another sensor, is to sort of like do a full sweep. So this is going to be the forward facing part. I'm going to do a full sweep like that to there and round and back again. We can't keep going round and round. The wires are getting a right angle. And we don't want to scan behind us because there's so many obstacles here that we get false readings. So we're only interested in this 180 degree sweep at the front. So let's upload the cord. Again, available on extronical.com. Link is in the description and they're popping up on the screen now. And it should start going in a second. In fact, it will if I actually connect power to the motor as well, which I haven't done yet. There we go. So you can see we're getting a 180 degree sweep. But it's not quite where I want it to be. It's not far off. But imagine if I unplug the Arduino at, let's say, that point there, plug it back in again, so you switch your device on and off, whatever it might be, your little robot or whatever it is. And when it starts up, where's its 180 degree sweep going to be now? Totally in the wrong place. So we need some sort of way of knowing when it's at this position, or converts to the other 80 degree position as a starting position. So we need to know, when is it there? So when is that sensor positioned like that? Then we can start our 180 degree sweep. Once we know a starting point like that, we cannot know at what point the robot or whatever it is was switched off, because you can't really track where that is. So we have to have some way of sensing a start point. And to do that, you could use a simple micro switch. So we'll just stop that moving, we'll just unplug that. So you could have a simple micro switch that's somewhere on your board that when this rotates, it presses against it and you know that's a known start point. However, I'm not a big fan of those. It takes quite a bit of force to press them, and I prefer a sort of non-touch approach. So what I'll be using is this little, these are like line follower little modules that will follow a black and white line on a piece of paper. They have an infrared emitter and an infrared receiver, so one shines out, and if you have something quite white or bright in front of it, it'll send a digital input to the Arduino. So if we attach some sort of piece of paper onto this sensor and we mount this in some sort of way, then when it rotates a certain position, we'll get a result on this, and we know we're at a certain start position then. This is a sensitivity control or potentiometer you can turn with a small screwdriver to adjust your sensitivity. So I'm going to mount that on now, and I'm going to alter the cord so that it will look for that and pulse backwards and forwards in the right sort of 180 degree phase. So before we try and add it in properly, we need to do a test of this little infrared device. So if you look round, we've actually got, keep this steady, we've got a supply voltage, a ground, and the signal out. And it's a simple yes or no, 0 or 1, high or low voltage. It's high, it sends out a high voltage if it's not seeing any reflection of this infrared. So the infrared sent out like that, and if it's not reflected back, this detects nothing and it sends out and keeps that high. If it detects something's reflected the infrared off there to come back into the sensor, it will send this low. When I've done, I've wrote a little sketch just to show that. So if you look here, I'll just wedge that up like that. You can see we've got a 1 currently being displayed. So we'll put this down here like that, we'll just hold that steady. And when we put something in front of it, it reflects and it changes it to a 0. And that's how we're going to actually detect whether the sensor is in the correct position. Okay, so I've now mounted the sensor to the board. You can see that I've bent up the infrared emitter and detector there, and I've blue tacked it onto the board. The signal, the out wire, is on this long blue wire into pin 6, and I've connected power and ground onto the local rails here, which I've made a tap to ground there from the Arduino, and I've jumped the power from that rail to this, so now we've got full power rails here and at the bottom. It should still be working. I've got the test code running, so you can see it's a 1, which means it's not detecting any infrared. If I put my finger in the way, you can see there's a 0. So when this rotates around, it should detect that, and we can actually know when it's got to that position there. So I'm going to write some code now, which will upload, which should make it go to the left first to find its start point, and then it will do once it knows that point, it will then do its 180-degree turn. Okay, here's the code. In the setup routine, the main bit we're interested in looking at is this. It's going to rotate the stepper motor anti-clockwise until that output pin of that infrared sensor goes low, or it reaches half a rev. Because at some point, if something's gone wrong, you don't want it continually rotating around, tangling up your wires. So if it's gone to half a rev, hasn't found it, it abandons it. So it does that, that's what that's doing, it's going around, and that will be quite slow when you're actually just doing it one step at a time in a loop. And there's an error. If it doesn't find it, it'll print up not found, start not found, and it will go into an infinite loop here, so we don't do any more code. But if it does find it, then it will start the main loop, and it will then instantly reverse at full speed, half a rev that way, and then the other way as well. So let's give that a go. I've already uploaded the code, so we just need to plug it in. You can see I've stuck on a small piece of white paper here, so that should go over the sensors with it. And look, I haven't actually tested this, I'm hoping it'll just reach the sensors, and that will stop it, and then it will rotate at full speed. So it will be quite slow to start with. Let's plug it in and see it in action. I've not tested it with this piece of paper yet, so this is the first test. So yeah, it is going quite slow, but hopefully when it goes over there, we'll see it go at full speed in clockwise direction. There we go, so it sensed it, and then it will do a full 180 degrees from there. And obviously what you want to do, you might want to adjust the position of your paper or that to get the sweep that you exactly want. But that's generally the idea. So now we've got a full sweep happening. All we need now, everything's in place. We just need to write the code that can look ahead, see obstacles, and if you're doing this for a robot, you could act upon them. All we're going to do now, for now, is display this on the screen as a sweep of the radar, like you see on a sort of aircraft screen of the radar. Okay, so here's the final build. When I power it up, we'll see the sensor sweep round to find its start point. And as we mentioned before, hidden, well, not hidden, but not quite easy to see, is the infrared sensor that will reflect off this piece of white paper here. So when that swings round, the white paper reflects that back, that infrared beam back down to the sensor. The Arduino knows that it's found the start point, and it does that pretty quick. It sweeps round, and then actually, because it's doing it that quick to get to the start point, I've programmed it so it then edges forward and then steps back in little steps till it finds it, just for accuracy. So it does a quick sweep back, but because it might have overshot a little bit, and then go forward a little bit, and then step back in very small increments. All that happens really fast, and you won't really notice it. It'll just swing round, and it'll start pulsing round and scanning the area. So let's switch it on and see what we get. I'm going to zoom in on this screen on the in post edit, and hopefully it'll be fairly clear. I don't know that as I'm recording this, but I think we'll be okay. So it's looking for the start, it's found the start, and it's tracking away. I'll repeat that again for you if you want. So we'll plug it in, watch it go around. You might notice it nudge forward a little bit and then reset itself. And then it's away. And you can see it's scanning like a traditional radar. You can see the beam scanning around to there and back, matching the scan of this. We can see a couple of blobs. And as it comes down, what this is going to be picking up on the actual leg of the tripod that the camera's on. So it's picking up a little bit on that. So we've got a little bit right close. It's also picking up, I think, the far tripod leg just a bit further away as well. So let's put something out there. We'll just wait while it goes past. Let's pop a small child's toy, and you can see it's picked it up. Now I'm going to try and stretch over. My arm might go in from the camera at any time. You can see that it's covering a reasonable area as well, which I'll explain that in a minute, but we are detecting this weeble, and from that distance, let's move it closer, and we'll see it's now picking it up a lot closer on that. Let's move it, we'll just wait while it's swept around again, and we'll move it further back some distance. And there it is, further back. You notice the arc is getting bigger the further back it goes, so I'll move even further back. And we're just picking it up on the edge of the detection. I've set this to detect up to 50 centimetres and no more. You could set it to 100 centimetres or 200 centimetres. I've set it to 50 because most robotic projects do not want to see beyond that. It's just too much information. So I've set it so after 50 centimetres, any object will be off screen and pretty much ignored. But you can see that's there, so I'm going to start moving it. Now you might pick my arm up as well in this, so you might get some spurious. I'm going to try and move it slowly forwards, and you'll see it on the scanner coming ever so slightly slow, moving closer and closer. Some of that will be my arm that it's picking up, my hand, but we can see it's getting closer every time until we get towards. So from that we can work out the distance that it is, and obviously, let's put it back to over there. Just watch the sweep again. Obviously, we can actually, it's getting a really big sweep on there as well for the size of the object, but we can move around. So if I move around there a bit, then that moves around there a bit. So we've got both distance and directions. Let's move it over there. Slightly out of camera shot, apologise, but we should be able to see it picking up on the screen there. So we can move it round as well. I'm doing that again now. You might come back into camera shots shortly. And there it is. And of course we can put that there, and we could have something else. Let's put that there. So now you can see we've got two objects that are in the scene. We could even have maybe a third a bit further away. Put that over there. And put that one there. So we've got three objects, two are out of camera shot. And I think it's not even picking that one up very well. Let's just turn that one. Yeah, so there we are. I was still picking up straight from the tripod as well. So that's it. But why are we getting these big beams? Let's just take these other two out. So we've just got the children's toy there. You can see that for the size of the object, it's quite a big section of line. If we move it closer, although it's blobby, that's the one in the middle there, ignore the other one, that's the tripod to the left. It's relatively small. Now move it to the far end of its ability to pick it up. It's covering a lot more area. And the reason for that is, and I'm just going to unplug this and stop it moving at a key point there. The reason for that is, and I'll put a graphic on screen now, the beam, the sound beam, actually spreads out, all waves spread out. And sound is, the lower the frequency, the more they will actually spread out. And that's why we use ultrasound, because that does actually narrow the beam a little bit compared to normal sound. But you can see we still get quite a spreading out effect. So we will pick up on an object that will appear to be bigger. The further away it is, the more we actually pick up on it and it will appear bigger. The ways around that are to have a more focused beam. So if you look on any sort of radar on a ship, it's not using sound obviously, but they have a dish, like a satellite dish, a parabolic dish, and that focuses their radar beam into a narrow beam. Now we could have some sort of dish going onto the sender, we could build one, but I don't really think it's worth the effort. It probably could even make it worse because the design of them is quite precise. But another thing we could do is actually use a radar sensor, which are available rather than the sound sensor. But if let's just plug it back in again. If your needs for your robot, whatever it is you're building, needs to see around its surroundings, if that's fine, that this resolution is okay, so we have one object more or less right in front, put another one over here. If that's fine enough for you to be able to work out your surroundings and work out where you are, then great, that's good. Otherwise, I am going to do a project where we basically replace this with a small radar sensor, which will have a much narrower beam, and we should be able to get more finite detail on that. But that's not going to be in the next couple of months or so. That could even be a bit longer than that before I get round to that part of this project. So that's it for now. Again, hopefully you can have a build of this and have an experiment, see if you can get better results than I have. Maybe a different manufacturer of radar sensor might be even better. But the link is in the link is in the subscription below as normal for the project on the website. And really appreciate it if you could like and subscribe. At the time of making this, I'm on 900 subscribers. It'd be great if I can get to 1,000 in the next month or so. So thanks for all those that have been supporting, watching my videos, and I'll catch you next time. So if you like that video, hit that like button. If you want to see more, hit that subscribe button. And the notification bell, make sure you get all the videos. And if you're that kind of sharing person, hit that sharing button. For a bit of laziness, if you haven't subscribed, look at the arrow, click on that icon, and it'll subscribe you. I haven't even scrolled down or anything like that. Is that it for this outro now? Yeah, I think so. Good.